Greetings to all of you here in Latin 2020. My name is Fabricio and I'm a doctoral student in Universidade Federal do Paraná, under advisory of Professor Marina Groshaus from Universidade Tecnológica Federal do Paraná and co-advisory of Professor André Guedes from Universidade Federal do Paraná. I'm here today to give a presentation on our work on Helly interval bigraphs and Helly circular arc bigraphs. These two classes are some of the main subjects of our thesis, and the results we include in this paper are some I consider to be particularly interesting. So, without further ado, let's start the presentation. First of all, circular arc bigraphs are a bipartite variation of circular arc graphs. So let's define circular arc graphs. Given a circle C and a family A of arcs over C, the pair CA is called a circular arc model. The corresponding graph of a circular arc model, called a circular arc graph, is the intersection graph of a family of arcs. Here we have an example of that. As you can see, for every arc on the model there is a vertex, and two vertices are neighbors precisely if their arcs intersect. For instance, A and E are disjoint, so they are not neighbors, but on the other hand, E and D intersect, so they are neighbors. Circular arc graphs are quite well studied class of graphs, with many interesting results spanning several decades. In this frame, we show just a small sample of the results that exist for the class. Another important concept for our work is the Helly property. A family of sets is said to be intersecting if every pair of elements in the family has a non-empty intersection. A family A is said to be Helly if, for every intersecting subfamily A-line, the intersection of the elements of A-line is not empty. For instance, here we have some examples. To the left we see a Helly family. As you can see, these three sets intersect each other and there's a common intersection in the middle, and to the right we see a non-Helly family. As you can see, the sets are pairwise intersecting, but there is no common intersection. The Helly property is used to define Helly circular arc graphs. A graph is a Helly circular arc graph if it admits a model CA such that A verifies the Helly property. Without going into too much detail, here we show a sample of works that exist on Helly circular arc graphs. Having presented circular arc graphs, we may now introduce circular arc bigraphs. A bicircular arc model is a triple CIE, where C is a circle and I and E are families of arcs over C. The corresponding graph of the model is constructed as follows. For every arc on either family, make a vertex. For two arcs A in I and B in E, their corresponding vertices are neighbors precisely if they have a non-empty intersection, and there are no edges between vertices corresponding to arcs of the same family, so the graph is always bipartite. The corresponding graph of a bicircular arc model is called a circular arc bigraph. In the following example, we represent one family of arcs inside the circle and another family of arcs outside the circle, with the circle itself being this dotted line. We use this representation for every bicircular arc model we are showing this presentation. Here we show a short list of works on circular arc bigraphs. Note that most results on the list are quite recent. Emphasize Groshaus 2019, where we introduce a polynomial time recognition algorithm for Helly circular arc bigraphs. Interval bigraphs are another important class for our work. They are a bipartite variation on interval graphs and a subclass of circular arc bigraphs. A bi-interval model is a pair of families of intervals on the number line, and the corresponding graph of the model is constructed as follows. For every interval in either family, create a vertex, and two vertices are neighbors precisely if their intervals are in opposing families and they intersect. And just like in circular arc bigraphs, vertices corresponding to intervals of the same family are not neighbors. And here we show an example. For every vertex, there is an interval and number line, with one family represented on top and another in the bottom. So here we show a very small sample of works on interval bigraphs. Needless to say, many more exist. So what did we do in our work? We introduce and provide a forbidden graph characterization of Helly interval bigraphs. We prove that they are a proper subclass of proper interval bigraphs. We introduce a forbidden graph characterization for the non-bichordal subclass of Helly circular arc bigraphs. We show that this subclass is also a subclass of proper circular arc bigraphs, and show that the number of bicliques on a Helly circular arc bigraph is linear on its number of vertices. So to introduce the Helly subclasses of interval bigraphs and circular arc bigraphs, we apply the bipartite-Helly property, which is basically a bipartite variation on the Helly property. A pair of families AB is said to be bipartite intersecting if every element of A has a non-empty intersection with every element of B. A pair of families EF is bipartite-Helly if, for every bipartite intersecting pair of subfamilies E-line in E and F-line in F, the intersection of all elements of E-line and F-line is non-empty. Note that the example we gave here is not bipartite-Helly, as there is no single number that is in all sets in both families. Using the bipartite-Helly property, we introduce Helly interval bigraphs. A bipartite graph is a Helly interval bigraph if it admits a bi-interval model AB, such that AB are a bipartite-Helly pair. Equivalently, G is a Helly interval bigraph if it admits a bi-interval model such that, for every biclique in G, the intervals corresponding to vertices of the biclique share a common point in the number line. So let's illustrate that with an example. As you can see here, a graph with its bi-interval model, such that for every biclique there is a point on the number line that all intervals corresponding to the biclique cross. The class is hereditary over induced subgraphs. A graph is in the class precisely if its twin-free version also is, and a disconnected graph is in the class as long as every connected component is in the class. The first result we present is a simple characterization that allows us to recognize Helly interval bigraphs very efficiently. A bipartite graph is a Helly interval bigraph precisely if its square is an interval graph. This result allows us to recognize Helly interval bigraphs by simply taking the square of the input graph and checking if it is an interval graph. So for our forbidden graph characterization, one may assume it is possible to get a complete set of forbidden graphs for Helly interval bigraphs by simply checking the square roots of forbidden graphs for interval graphs. This approach, however, is problematic. For instance, not every forbidden graph for Helly interval bigraphs is such that its square is minimally non-interval. Instead, we use a more direct approach, which also provides greater insight on the structures of Helly interval bigraphs. The forbidden graphs we use are the T2, the X2, the domino, and every even cycle of length greater than 4. In order to prove our characterization, we use a special type of graph we call interval theorem graphs, composed as follows. We start with a path P1 to Pk, we then add leaves to every element of the path except P1 and Pk. For every I between 2 and k-2, we add vertices Wi from Wi1 to Wini for some Ni, neighbors to Pi, so you can see here P2 is neighbor to W21, W22, and so on. We then add vertices Ui, neighbors to Pi plus 1, as you can see P4 is neighbor to U31, U32, and so on. And then we finally connect the W's and U's in the following way. Every Wij is neighbor to all Uil for L less than or equal to j. For instance here, in W2, W21 is neighbor only to U21, W22 is neighbor to U22 and U21, and W2 and 2 is neighbor to all of U2. So, for our characterization, we show that every ITG is a Helly interval bigraph, and use this fact to prove that a bipartite graph is a Helly interval bigraph precisely if it does not contain any of the forbidden graphs we cited before. The proof consists of showing that every twin-free connected bipartite graph without any of those graphs is an induced subgraph of an ITG, and then fill in some other details. So, moving on to the proof that Helly interval bigraphs are a subclass of proper interval bigraphs, a bipartite graph is a proper interval bigraph if it admits a bi-interval model AB such that A and B are proper families, that is, families such that no two elements are contained in one another, as in the following example. Note that the intervals above and below the number line do not contain each other. The class is hereditary, closed for the addition of twins, and such that a graph is in the class precisely if every connected component is. The proof that every Helly interval bigraph is a proper interval bigraph consists of showing that every ITG is a proper interval bigraph, and then using the fact that every twin-free connected Helly interval bigraph is an induced subgraph of an ITG, and then fill in some details. Moving on to Helly circular arc bigraphs. A graph is a Helly circular arc bigraph if it admits a bicircular arc model CIE such that IE is a bipartite Helly pair. That is equivalent to there being for every biclique on the graph a point in the circle such that every arc corresponding to a vertex in the biclique crosses that point. So here we have an example of a C6, and as you can see, for every biclique we marked a point in the circle with these lines radiated from the center of the circle, indicating the point all arcs corresponding to vertices of that biclique cross. The class is hereditary and closed for the addition of twins. As I previously cited, in 2019 we introduced a recognition algorithm for Helly circular arc bigraphs. It is separated in two cases. The C6-free case, where we simply take the square of the graph and see if it is a circular arc graph, and the case where the graph contains an induced C6, in which we introduce a forbidden graph characterization. Now, non-bichordal Helly circular arc bigraphs are simply graphs that are both Helly and non-bichordal. That is, they have at least one induced cycle of length greater than 4. So our characterization of non-bichordal Helly circular arc bigraphs is basically a generalization of the C6 case from 2019. Also, as we'll see, it is analogous to our characterization of Helly interval bigraphs in many ways. The forbidden graphs we use are the T2, the O2, the BW3, the O4, and every even cycle of length greater than 4, plus an isolated vertex. So, in order to prove our characterization, we introduce a type of graph analogous to ITGs, which we call circular theorem graphs. We start with an even cycle of at least 6 vertices instead of a path, with leaves on every element of the cycle, set Wi neighbors of Ci, set Ui neighbors of Ci plus 1, and every Wij is neighbor to every Uil for L less than or equal to j, just like in ITGs. We show that every CTG is a Helly circular arc bigraph, and then use this fact to prove our characterization. We basically show that every twin-free, non-bichordal bipartite graph without any of the forbidden graphs we cited is an induced subgraph of CTG, and the rest is details. So moving on to the containment proof, a bipartite graph is a proper circular arc bigraph if it admits a bicircular arc model CIE, such that I and E are proper families. The class is hereditary and close to the addition of twins. The proof that every non-bichordal Helly circular arc bigraph is a proper circular arc bigraph is analogous to the interval case. We show that every CTG is a proper circular arc bigraph. As you can see on the frame, there are 2 different ways to do that, and then fill in some more details. It is important to note, however, that for the bichordal Helly circular arc bigraphs, the containment doesn't hold. The graph we show here is Helly, but not proper. For the last result of our paper, we show that Helly circular arc bigraphs of order n have a linear number of bicliques. The proof is separated between non-bichordal and bichordal graphs. For the non-bichordal case, we show that every CTG has a linear number of bicliques, and then show that the number of bicliques in every bipartite graph is equal to the number of bicliques in its twin-free version, and the rest is details. For the bichordal case, we use the fact that every C6-free Helly circular arc bigraph is such that its square is a Helly circular arc bigraph, such that the number of cliques in the square is equal to the number of bicliques in the square root, and we then employ the fact that every Helly circular arc graph has a linear number of cliques. So in conclusion, we showed forbidden graph characterizations for Helly interval bigraphs and non-bichordal Helly circular arc bigraphs. We proved that every Helly interval bigraph is a proper interval bigraph, and that every non-bichordal Helly circular arc bigraph is a proper circular arc bigraph. And then we showed an upper bound for the number of bicliques in Helly circular arc bigraphs. Thank you all very much for watching. If you have any questions, I'll be in the chat. I really appreciate it. Thank you.
Thank you, Fabricio, for your talk. And I wonder if there are any questions or comments.
I have a question.
Please.
What about the intersection of the student classes with planar graph?
Oh, your microphone is turned off.
Who?
Mine?
Oh, I see.
Okay. I'll make again. What about the intersection of the student classes with planar graphs?
Can you repeat the question?
Of course. What
Please.
about the
Couldn't hear the question.
of the student
Your
classes
microphone is still turned off, actually.
with planar graphs?
Intersection with planar graphs?
Yes. With
Oh,
the
I have not
student
checked that
classes.
yet, actually. Sorry. I still can't... Is the microphone still off? Because I can't hear him. I'm sorry,
Okay.
I can't even...
there's a problem where perhaps if you leave the microphone and go back again, it will work for Fabricio.
Okay, I will
Let's
make
try
a
this.
reset. Just a minute.
Connecting. Well, okay, finally, yeah.
Okay.
Okay, now I hear you.
Can
I'm
you hear
sorry.
me? My point is, what about the intersection of the studied classes with planar graphs?
Oh, I have not studied that actually, but it's something to be thought about. It's pretty interesting, and in fact, I believe it is possible that might be some interesting developments in that, but I have not looked into it yet.
Okay, thank you very much.
Okay, thank you. Thank you for the question.
And congratulations for the nice talk.
Oh, thank you. Thank you, Professor.
It was very nice. Thank you.
Thank you, Professor.
Yes, it was a nice talk, very vigorous.
Thank you, Professor.
Very nice. Well, let me ask a question. I'm asking the chair if I can ask. Okay. You did not define unit circular arc bigraphs, correct? Can you define that?
Unit circular arc bigraphs.
Unit circular arc bigraphs, yes.
Basically, circular arc bigraphs that admits a model where every arc is of the same
Yes, I
arc.
know. But you, my question, I think it's probably yes. If with circular arc bigraphs happen the same thing as with circular arc graphs, that proper equals unit.
Actually, no. As far as I know, because there is one, I believe not at least. I believe the answer is no, because there's one paper in particular that has like two separate characterizations for unit and proper circular arc bigraphs based on matrices. Obviously, unit is a subclass of proper, but I don't believe the inclusion. But I don't believe it is equivalent. I'm not entirely sure though. That's something to be seen, but I believe it isn't because I've seen this one paper that I have separate characterizations that, as far as I've checked, they're not equivalent.
Okay, thank you.
Thank you, Professor.